pH values and acid-base calculations. Water is associated with many properties of living things, including the phenomenon of acids and bases. Water is considered to be the solvent of life because of its importance in living reactions. Water can exist in all three physical states, solid, liquid, and gas, in the presence of living cells and living things. And the main relationship between water and biochemical life reactions is that almost all biochemical reactions in living things must happen in the presence of water, either immersed in water as an environment, or it produces or consumes water molecules as the reactions progress. Water molecules, like all other compounds in a solution, will collide with one another as they are present in that solution. The higher the temperature, the stronger the collisions. But at room temperature, where the water is liquid in form, water molecules will either be intact, as shown on the left, or during these collisions break apart into the two species shown on the right. The hydroxide ion and the hydrogen ion are the two parts of the water molecule that contribute to what we consider to be acidic or basic conditions. The hydroxide ion is negative in charge, having extra electrons, and the hydrogen ion is lacking electrons. Both of these ions, or charged particles, will react with other compounds or atoms or whatever it can come in contact with in order to react to try to become stable once again. So the water molecule on the left is stable as an intact compound, and the ions on the right are highly reactive. So the amount of hydrogen ions contributes to how acidic a solution is, and the hydroxide ions contribute to how basic a solution is. So we can kind of determine a scale of numbers to try to describe how acidic or basic a solution is. And so that scale is named the pH scale. And pH literally refers to the power of hydrogen. The pH value is based on the relative concentration of hydrogen ions to hydroxide ions in a solution. So the important word here is relative concentration. If we compare the amount of total hydrogen ions to the amount of total hydroxide ions, that ratio is what determines the pH value. As we mentioned earlier, the water molecule dissociates or comes apart into hydrogen and hydroxide ions naturally in a glass of water or in any liquid state. And so at any one time we can describe and measure exactly how much of water at any one time is broken into the two reactive species. Now the pH does give us an indication of the difference in the concentration of these two ions, but it doesn't necessarily give us a really good indicator of how strong the acid or base is. So this note, it's important to understand that the strength of an acid or base is determined by the absolute concentration of hydrogens and hydroxide ions. And so the strength then is based on the amount of imbalance. Let's take pure water, for example. The pH of pure water, we look at it this way. In 1 liter of pure water, we measure on average 1.0 times 10 to the minus 7 moles of water molecules will be dissociated into the two reactive species, hydrogen and hydroxide ions. So anytime we're looking at pure water in a container, 1 liter of it will have this many molecules that have been dissociated. The rest of the water molecules will be intact compared to those. If you're unfamiliar with the molarity concentration descriptions, let's have a quick review of chemistry. 1 mole is equal to 6.02 times 10 to the 23rd items or objects, or in this case molecules. If we write out the entire number with all the zeros instead of the scientific notation, you see how big of a number this is. It's not practical to write this number over and over again as we're doing chemistry calculations. So instead, we use the scientific notation 6.02 times 10 to the 23rd equals in a reaction. So if we have 1.0 times 10 to the minus 7 moles, is actually equal to 6.02 times 10 to the 16th molecules or ions. So that means that in 1 liter of pure water, there are 6.02 times 10 to the 16th hydrogen ions that are present, and 6.02 times 10 to the 16th hydroxide ions that are present. And if all of these were to recombine together, each and every pair would produce another intact water molecule again. The pH equation shown allows us to calculate the pH of a solution if we know the exact concentration of hydrogen ions. So if you have a calculator, you'll need to locate the log 10 button. Okay, so usually it's just labeled as log. Let's suppose we want to calculate the pH of pure water. Since we know that there are 1.0 times 10 to the minus 7 moles of hydrogen ions in 1 liter, that's what the brackets in the equation represents, the hydrogen ion concentration. Then plugging in those numbers and hitting the log button on your calculator will simply return the numbers minus 7. And since the pH is the negative of whatever the result of the log function is, then negative 7 is a positive 7. So if you look at this carefully, what you see is that the 7 is related to the 7 in the power of the 1 times 10 to the minus 7. So in other words, just to kind of get a quick idea of what the pH value is, it's the negative of the power. Notice 7 minus 7. And this is true if the number in front of the scientific notation is just 1. So when we have equal amounts of hydrogen ions compared to hydroxide ions, the pH value will be 7, and this indicates a neutral condition. Neutral where even though we have hydrogen and hydroxide ions, the liquid itself will not be reactive because we do not have an imbalance in the number of hydrogens and hydroxides, even though they are broken apart. So let's try this out. Go ahead and try using the equation to solve this problem. If the hydrogen ion of a solution is known to be 4.25 times 10 to the minus 3 molar, that's what the big M stands for, or moles per liter, what would be the pH value? So go ahead and hit pause and try this problem out, and then in the next slide you'll see the answer to check your work. Okay, let's take a look at the answer. Remember that the equation is pH equals negative log concentration of hydrogen ion. Since we know it's 4.25 times 10 to the minus 3, enter that into your calculator and then hit the log button to produce the log function. Your calculator should return the number negative 2.37161107, and then we want to take the negative of the negative number, which simply turns it into the positive value. And if we look at the number of significant figures in the original problem, 4.25, we need to round off to 3 significant figures. So you should have 2.37 as your answer for the pH. Again, notice how this number, 2.37, is very close to the negative of the exponent value. Remember, we consider pH to be the power of hydrogen. In other words, to what power of 10 are we raising a number to try to describe the acidity or basicity of a solution? Okay? When this number is not 1, then this number is not going to be exactly equal to the power. But you can see that it's close. So that's kind of one way you can check to see if you're doing your math correctly. The pH scale then ranges from 0 to 14. At the lowest 0 and at the highest 14. Here we can take a look at a pH scale in terms of powers of 10. We mentioned earlier that a neutral pH is represented by pH 7. So as you can see, the 7 represents the 10 raised to the power of negative 7. So the higher the concentration of hydrogen ions compared to hydroxide, the smaller the number becomes. So this number right here, the value of the pH drops or decreases. So the more acidic a solution is, the lower the pH value. Basic solutions contain more hydroxide ions than hydrogen ions. So as we increase the amount of the hydroxide ions, by a relative amount we will be decreasing the hydrogen ions. And that affects the pH value by increasing the value, the exponent value. So now we're going to have a greater pH associated with bases. So everything is relative to 7. When we say high pH versus low pH, we're talking about starting at 7, are we going up or down from that value? If we begin at pH 7 and then we add enough hydrogen ions to make the solution pH 6, what we had to do to accomplish this is to increase the amount of hydrogen ion by 10 times more. So pH 6 has 10 times more hydrogen ions than pH 7. By the same token, if we go from pH 6 to pH 5, pH 5 has 10 times more hydrogen ions than pH 6. So what does that mean if we go from pH 7 to pH 5? Is that now we are increasing the amount not just 10 times, but 10 times 10. So that's 100 times. So if we go and change 2 pH units, the difference between the original and the new pH value is now 100 times. How many times more hydrogen ions would you have compared to hydroxide if we went from pH 7 to pH 4? That's right. It would be 10 times 10 times 10, or 1,000. And if we look at it in the other direction, going from pH 9 to pH 10, now we're going to be 10 times less hydrogen ions in comparison. Or another way to think about it is each step going in an increase, we're going to be increasing the amount of hydroxide ions by 10. So pH 8, for instance, compared to pH 7, has 10 times more hydroxide ions and 10 times less hydrogen ions compared to pH 7. Practice using this equation to calculate the pH of any unbuffered solution based on its hydrogen ion concentration. There's something else we can do with this equation, is that we can actually rearrange or rework the equation to find the hydrogen ion concentration based on the pH. So if I tell you what the pH of a solution is, you can actually determine what the exact hydrogen ion concentration is in that solution. And the way you rework the equation is this. Now what's happening here is the hydrogen ion concentration will be the answer when you use this button on your calculator. 10 to the power of x is referred to as the anti-log function. Usually you can hit Shift and the log button, and that should be the opposite inverse function. It should be the anti-log. So let's try it out. Let's suppose we have a pH of 9.02. What is going to be the hydrogen ion concentration? Use the new equation that was shown on the last page. And go ahead and pause. Pause the video and then try this out, and then let's check the answer. Okay, let's go over the answer. So, if we use the equation hydrogen ion concentration is equal to the anti-log of the negative pH, we need to enter into the calculator negative 9.02 and then hit the anti-log function button. The answer should come out 9.5499 and so on times 10 to the minus 10. The units of concentration are moles per liter. And since we again have three significant figures, we're going to round off to the third place. And so then our answer becomes 9.55 times 10 to the minus 10 moles per liter. And you can use big M to represent this moles per liter. Both of these are equivalent. And this is oftentimes how you'll find molar concentrations described in your reading in your text and on chemical labels. So now that we're done with this, let's go ahead and go through some review questions. What does the pH of a solution tell you? Does the pH of a solution alone tell you how strong of an acid or base it is? What are the two ions that water dissociates into? What is the equation used to determine the pH of an unbuffered solution? What is the range of pH values, and how can you tell if a solution is neutral, acidic, or basic based on that value? How do you calculate the hydrogen ion concentration from the pH value of a solution?